In the AP Stat syllabus, you'll see something that says, hey, we need to understand the effects of unit changes on summary data. Break it down. Unit changes are changing from like feet to inches, multiplied by 12, or minutes to seconds by multiplying by 60. Summary data would be things like means and standard deviations. So what we're talking about is what happens to means and standard deviations and IQRs when we make a unit change. Well, that's a good question. We'd like to know. So here it is. Let's first grab a practical understanding of this, and then we'll go into a more formula-based approach. So here it is. Let's suppose we only have 8 students in a class. These are test scores. So our variable is the test scores. The mean of the test scores is 80. Standard deviation is 9.87. Well, then we say, okay, now what happens if we take all these test scores and add 10 to it? This is a linear transformation, taking all the scores and adding 10. Well, what's going to happen to the mean of this transformed data? So we subscript it like this to say that. We'll think it through. All the scores had 10 added to them, so if every score is 10 units bigger, then the new mean should be 10 more than that guy. So the new mean should be the old mean plus 10. There's your formula right there. Okay, then the standard deviation, if all the scores are just shifting up 10 units, do you agree the scores are no more spread out than they were before? So measures of spread are unchanged when you add a term to all of the scores. Look at the dot plot. You see that the black dots, the original data set, are just as spread out as the red dots, which is the transformed data set. So the spread is not changing. And actually, probably the most practical way to look at it is pick any 2 adjacent scores. The 79 and the 80. I'm sorry, the 79 and the 81. When you added 10 to each of those, they're now 89 and 91. Do you see that the gap in between is still 2, just like the gap in between these before was also 2. So the spread does not change when you add. But what happens if you multiply? In my class, our tests are worth 1,000 points. So if I initially graded them out of 100, I thought, oops, I made a boo-boo. Let's change this to out of 1,000 by multiplying all the scores by 10. So the new transformation of the variable would be multiply all the scores by 10. So if all the scores are getting 10 times bigger, the mean average should be like in between these guys like it was before. So it's 800. So the new mean is the old mean average, the original use of x, multiplied by 10. So the mean gets multiplied by 10. Will the standard deviation change? Will the scores be more spread out than they were before? And the answer, yes. Again, take any 2 adjacent scores like 79 and 81. They're 2 units apart. But now how far apart are they? They're 20 units apart. They're 10 times more spread out than they were before. So the measures of spread will change when you have a multiplier by all the scores that make up that variable. Now check it out, you can see it on a dot plot. See this? These are all the transformed scores that are spread out between 620 and 950. But the original scores are spread out between 62 and 95. So not much spread there, 10 times as much spread here. So if we keep that in mind, we can come up with a formula for linear transformations. If the random variable x is going to get transformed by multiplying it by a factor and adding a term to it, then the new mean, the mean of this transformed variable, we subscript it like this, would be to take the factor of a times the old mean and then go ahead and add to it. So in the problem that we just got done doing, we'd say, oh, we could multiply all the scores by 10 and then add 10 to it. So we'd multiply the original mean by 10, and that took us to the 800, and then we'd still add 10 to that, so the final result could be 810 if we did both things. But what's going to happen to standard deviation? Remember, it's only the multiplier that affects the standard deviation, not adding a term to it, because that just shifts the value up or down. The scores are no more spread out. So when it comes to standard deviation of the transformed variable or the transformed random variable, the only thing that's going to change is the old standard deviation is going to get multiplied by a, by that factor. The b, the thing that's being added, will not affect it. Okay, let's look at a practical example. Let's suppose we got people doing the long jump, right? Whee! They're doing pretty good. But we said, you know what, that's boring. Let's teach jackrabbits to do the long jump. So here we go. All right, boing, 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 woohoo! They don't go very far, but hey, it was fun because we got a bunch of jumping jacks. That's really cool. So we're getting some exercise. But anyways, here's the problem. The poor jackrabbits, they're going to have their self-esteem hurt because the humans are jumping, whoa, long way, many, many feet, okay? But the jackrabbits, look at that, that's pathetic, okay? Their mean average jump is only 2.2 feet with a standard deviation of 0.8 feet. We have to make them feel better about themselves. So what we're going to do is, let's convert the units from feet to inches. Unit changes. So to go from feet to inches, we multiply by 12. So that ties in what we just got done doing. So think about it. What's going to happen to this mean average and this standard deviation when we multiply by 12? When you multiply, both measures of center and measures of spread change. So what's going to happen? Changing from feet to inches, a unit change. How will it affect the summary data? Well, the sample mean will get multiplied by 12, and the standard deviation, sample standard deviation gets multiplied by 12. So the new mean is going to be 26.4 inches, and the new standard deviation is going to be 0.96 inches. But hold the phone. Do we see that little patch of grass between the takeoff ramp and where we started measuring? Holy smokes! If these little buggers came boing, 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 and jumped from the takeoff ramp and landed 2 feet away, they also cleared the 1 foot patch of grass before they got into the pit. So here's the deal. Not only do we have to multiply by 12, but we got to add a foot also. So the new random variable is going to get transformed this way. We have to multiply by 12 inches to convert from feet to inches and add another foot, but now that we're in inches, that means we're going to add 12 inches to that. So this would be our linear transformation right here. Now you could look at it another way. The original scores need to have a foot added to them to make up for that patch of grass that's a foot long. They actually jumped a foot longer than what we had measured. But then you could take that result and multiply it by 12, and the distributive property would still get this linear transformation on the data. So what's going to happen to these guys? Do you agree that the 12 will have to get added to the mean to give you a new mean of 38.4? But check it out, by adding that foot, and that must be fortunate for the rabbits, it's got to be lucky, we're adding a rabbit foot. That wasn't funny. Anyways, so what's going to happen now? Check it out. When we multiply all the distances by 12, and then we add that extra foot, adding that foot, does that make the results any more or less spread out? The answer is no. So adding the 12 has no consequence on the standard deviation, so it stays at 0.96. Measures of center change no matter what you multiply or you add, but measures of spread are only affected by multipliers. So, to summarize, let's say we're looking at swimmers that are holding their breath. That's the random variable. We're measuring how long can they hold their breath. The unit of measure is minutes. This is the summary data for all these things. We have the measures of center and the measures of spread. Now, we want to change this to seconds. And so, do you agree the new units, being seconds, are going to take that original variable and have everything multiplied by 60? Since we're multiplying, all the measures of center and spread will be affected. So we're going to take 60 times this, we're going to get 96. 60 times this, we're going to get 84, that's an 8. 60 times this is going to be 60. 60 times this is going to be 30. And we're going to hold off on variance for just a second. Let's go down to IQR. That's also 60 times bigger. That goes to 48. And this is 60 times bigger. That goes to 132. Do we agree that variance is the square of the standard deviation? So the easiest thing to do is to take the new transformed standard deviation and square it to get the new variance. So the new variance must be 900 because it's the square of the new standard deviation. So this is the new standard deviation squared. Now, look at something very carefully here. How do you go from the original variance to the transformed variance? Well, all the scores got multiplied by 60. When you multiply this by 60, you only get 15. So that can't be the right answer. We can't multiply the old variance by 60. Since the variance is the square of the standard deviation, we have to multiply this guy by whatever A is squared. So 60 squared is 3,600. If we multiply 3,600 times 0.25, that'll give us 900. My suggestion to you, change all the different data, don't mess with variance. Once you get the new standard deviation, just square it to get the new variance. And if you want to look at that real quickly, it's just like this. If the original x gets transformed to be multiplied by 60, we go from this to this, and the new variance would be this guy squared, which is 60 squared times sigma squared. So that's why the new variance has to get multiplied by 60 squared, but the new standard deviation only gets multiplied by 60. So then, one last deal. Here's what I suggest. Instead of taking this guy and multiplying it by 60 squared, we might be more likely to make a boo-boo. So my suggestion, what I like to tell you, is if the original standard deviation was 10, and the transformation is to multiply by 60, then do this first, go boing, change it to here, and then once you have the new standard deviation, just square this thing to get the new result, which 600 squared would be 36 with 4 zeros after it. You've got your final answer. I think that's a little less risky than starting here and remembering to multiply not by 60 but by 60 squared. You'll get the same answer. I think that's my preference that way. But there you go. That's an idea of how it works when we change units and how they will affect the summary data.